Hello class, this is a test. I just wanted to do this video this way, and I will see if it doesn't look good, if you guys can't make out the screen very well or it's poor quality, if you can't hear me, just let me know and I will try to change some things up for the next video. I wanted to start with the home page for Canvas, just to run through a few things that you might need for each lesson. So if you're at the home page, then you should be going to week 2. So week 2 is here, and it has the discussion questions first and last, and then right in between are all the PowerPoint presentations. You can also typically find these under the files for the course, and the files are over here on the left. Okay, but I'll go back down to the first one, and if you want to follow along with me using the PowerPoint, or you just want to go back and refer to it later, you can do so. So I'll open this up and we will begin. So some tips for taking notes along with me. Of course, this is a video, so if there's something that you didn't quite catch, definitely pause and come back to it. Also, make sure that you are taking notes. Even though you have the slides here, I may say something that is not on the screen. So be sure to jot down anything that you hear that's not on the screen, and then email me or a classmate if something sounds confusing. So let's go ahead and get started. So we're going to start with chapter 2, set theory, and this is the first section of that chapter. So here are objectives that we will cover. There are quite a few, but most of them are pretty simple. So a few definitions to begin with. Of course, we need to know what a set is, and it is a collection of objects whose contents can be clearly determined. So you know what a set is from just using that term in everyday language. But here we can hone in on the definition a little bit more than what we would regularly use. We need to define a set, and here we say that it's well defined when the contents of the set can be clearly determined. And so, of course, in layman's terms, if I can define my set so that other people are clear on what's in it, there's no question, then it's well defined. We see another term here called elements or members, and those are the objects in a set. So I can, for example, say that I have a set of bicycles. And so the elements in the set would be the bicycles themselves. Maybe I color coordinate, or there's a special feature about some of the bikes that are in common or different. And so I can talk about the elements or members of my set in this way. So methods for representing sets. We typically use capital letters to represent a set. And we can, of course, describe the set using a word description. Or we can list the elements of the set, and that's another way to define the set as well. So the example given is W, a capital letter, which will represent the set of days of the week. And then the roster method is listing those days of the week: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So as you notice, we use braces for the grouping of those elements, and we place commas between each element so that the reader knows these are individual elements. So braces and then commas. So here's an example. So write a word description of the set. P is equal to, and then there are 5 names there. Well, if you know anything about our history, our U.S. history, then you'll know that all of these names are names of presidents. And not just presidents. Remember, we want the set to be well defined. This is the set of the first 5 presidents of the United States. So we want to be as clear as possible, making sure that if there is any descriptor that we can use to describe this set, that we'll use it so that those reading will know exactly what we are talking about. So the same with this example. We have the set C, which is the set of U.S. coins with a value of less than $1. And in roster form, we see those listed at the bottom. Having fun yet? A set builder notation is a way also that we can describe the set without listing all of the days. So there's common language that we use here. And of course, we have a capital letter to represent the set. And we still use braces, but inside or between the braces, we see a description, a word description of that or for that set. So set W is the set of all elements X, such that X is a day of the week. So each of those pieces are there pointed out as to what they mean in terms of this set. Of course, we can go from set builder notation to roster notation, and from roster notation to set builder notation. So in this first example, we have a set in set builder notation, and it is the set of all X such that X is a month that begins with the letter M. And of course, there are only 2 months that begin with the letter M. And in roster form, under the solution, we see those 2 months. The empty set sounds just like what it is. It's a set that is empty. So we also call it the null set. And you see that denoted by braces with nothing between them, or the circle with the slash through it. So here's an example of an empty set. The set of all numbers less than 4 and greater than 10. So the difference here is that word and. So the set of all numbers less than 4 and greater than 10. If we wanted to make it a set with values in it, we could say or, but and means that there's an intersection. And obviously there are no numbers that are less than 4 and greater than 10. It just does not exist. An example at the bottom there may be even a little bit more clear. This one is the set of all X such that X is a fawn that speaks. So I don't know any fawn that speaks. So that would be an empty set. At least not in this world, maybe in Narnia. So which of the following is the empty set? So the answers are there for you. So 0, or the set that contains 0 in it, obviously is not empty. 0 is a number. It's a valid value. Hence, that set is not empty. There is one element in it. And B is not a set at all. 0 is just a value. Unless we put braces around it, it is not a set. Here are two more examples. So we have C, which is the set of all x such that x is a number less than 4 or greater than 10. So these words, these keywords are very important when identifying well-defined valid sets. So in this case, this set actually does have numbers in it. There are numbers that are less than 4 or greater than 10, and those numbers can be listed. The last is the set of all x such that x is a square with 3 sides. I've never seen a square with 3 sides. There is no such thing. So in this case, the set is empty. So here again is more notation. And so it will be very important for you to go back and review all of these new symbols and terms so that you can be sure to recognize them when we use them for homework and for tests and in-class discussion. So the symbol, this fancy E, is used to indicate that an element or an object is an element of a set. The symbol is used to replace the words is an element of. The symbol, the fancy E with the slash through it, is used to indicate that an object is not an element of the set. So again, more examples. So we have to determine whether each statement is true or false. So is R an element of the set? And it looks to be letters from A to Z. Well, obviously, if it's the alphabet, then R is definitely an element of that set. The ellipses in between C and Z represent a continuation of those elements. So we go from A, B, C, and to save space and time, we put the ellipses there so that everyone who reads this understands that the set will continue until we get to Z. So in B, we have 7 is not an element of this set 1, 2, 3, 4, 5. So is 7 an element of that set? Definitely it is not. 7 is not in that set. So that statement is true because of the symbol that's used. The last is tricky, but hopefully you'll understand that the set with A in it is not an element of the set with A and B in it. Some common sets that we see in mathematics are the set of natural numbers. So the natural numbers are whole numbers, no decimals, excluding 0. So we have 1, 2, 3, 4, 5, and then you see the ellipses again to tell us that this set continues on infinitely. There is no endpoint for the natural numbers.